Over the next few moments, we're going to have a look at the concept of moments and in relation to forces, and we're going to link back to the work we've done on forces as well. So, a moment is associated with a force. A moment is the tendency for a force to create a turning motion. So if I push on something, then as long as there's a net force, as we know through Newton's first law, it's going to create some motion, it's going to create acceleration. Now, depending on exactly where I'm pushing that object, it may also cause that object to start rotating. And the theory behind moments allows us to make predictions about that, or at least determine when we'll have a rotation and when we won't. So we'll start by defining exactly what a moment is. So the moment of a force is that force multiplied by the perpendicular distance of that force from a pivot. So here we've got a force acting upwards, and it is some distance from this pivot. So this force F times this distance x gives us a moment m. And this allows us to add a little bit to our definition of equilibrium. So previously we've said that for a force to be an object to be in equilibrium, we need the net force acting on it to be zero, i.e. the sum of the vertical forces and the sum of the horizontal forces to both independently be zero. But now we can also say that the sum of the moments acting on an object must be zero. And exactly what it means for an object to be in equilibrium with respect to moments is defined a little more detail through the principle of moments. The principle of moments says that for an object to be in equilibrium, the sum of the clockwise moments acting on an object must equal the sum of the anti-clockwise moments. So when we have a moment like we've got here, we can see this one is acting anti-clockwise. Now another moment might be acting clockwise. So for this object to be in equilibrium, we must have the anti-clockwise moments equal to the clockwise moments. There's also a special case of moments, and that's something called a couple. So when we've got two forces which are equal in magnitude and anti-parallel, so acting along the same line but offset from each other and in opposite directions, then this is what we call a couple. And this only produces a rotation. It doesn't produce any linear motion, because of course the net vertical force on this is going to be zero and there's no horizontal force. So it produces just a rotation, no linear motion at all. And the moment created by this couple, or the torque created by this couple is given by one of the forces times the distance between them. So in this case we've got two forces, each of F acting with a distance d between them, and the torque of that is going to be Fd. So let's have a quick look at a short example of how this can be used. So let's take a nice simple seesaw, for example. So here's our seesaw, perfectly straight, and it's pivoting around the centre. And I stick something on this seesaw, like a child, let's say 30 kilos, and I position it 1.2 meters away from the centre of the seesaw. We can calculate what the moment exerted by this child is, and that's just going to be this force here multiplied by the distance from the pivot. So we do the 30 times by the 1.2, and we get a moment of 36 Newton meters. So that should be 30 newtons, not 30 kilos, which is actually now only a 3 kilo child, but we'll run with it. So 30 newtons acting downwards, 1.2 meters from the pivot gives us 36 Newton meters. So newtons times meters gives us units of Newton meters. So that's our moment, and it's acting clockwise. So let's put a little c under there. Now if we wanted this to be in equilibrium, we'd have to put another object over here so that that can act downwards in an anti-clockwise direction, and we'd have to have, depending on its weight, we would have to position it to make sure that we balance. So let's say we've got another object, and this one is 50 newtons. And this is acting somewhere, some distance from this pivot. And we want to know where exactly is that, so that by the principle of moments we are in equilibrium. So we want the anti-clockwise moments to be equal to the clockwise moments. So the moment of this 50 Newton force is going to be the 50 times by the x. We want that to be equal to the 36, and so we can see our x is going to be 36 over 50. And that gives us a distance from the pivot of 0.72 meters, or 72 centimeters. So if we position this 72 centimeters or 0.72 meters away from this pivot, then the moments acting on this seesaw will be balanced. That doesn't mean we're actually in equilibrium yet. Remember, equilibrium requires the principle of moments to be satisfied, so the clockwise and the anti-clockwise moments to be balanced, which we've done by carefully positioning our 50 Newton force. But it also requires that the net force acting on the object is zero, so no net moment as well as no net force. And we can see so far, with just these two forces, we've got a net force of 80 newtons acting downwards. So we know we need, in order for this to be at equilibrium, 80 newtons acting back upwards somewhere. But we've already balanced the moment, so how do we position this 80 newtons on this seesaw somewhere so that we don't introduce any additional moment and mess up the moments? Well, we know that a moment is given by a force times the distance from a pivot. So if we set this distance to be 0, then regardless of what the force is, our moment will also be 0. So if we position this 80 Newton upwards force on the pivot, then it will introduce no further moment because the distance from the pivot is 0, but we can still have the 80 newtons acting upwards to balance our 50 and our 30 Newton forces. So this is how we can use our principle of moments to make nice simple calculations about what the moments are that are exerted by a force. So we calculated the moment exerted by this 30 Newton force, and how we can then balance it by working out where to place the force. Or similarly, we could have known a distance and worked out what force we needed to place, and then we added in the little bit extra that we know about how to bring something to equilibrium to realise that we needed also an 80 Newton force acting upwards at the pivot to bring this object completely into equilibrium and have all the forces balanced as well as the moments balanced.